Okay, we're going to talk about horizontal projectiles in this problem. Hopefully you've already viewed the videos about the basics behind horizontal projectiles, and we're going to use those concepts as we solve these problems. This is a projectile that's launched horizontally. That means it begins its projectile or its trajectory in a completely horizontal direction, as opposed to projectiles launched at an angle, which we'll talk about in another set of videos. So let's read this problem, and we'll use that problem to explain how to solve problems like this. Wile E. Coyote, he's now obeying the laws of physics as opposed to what he most of the time does in his cartoons. He runs off an 80-meter high cliff at a speed of 18 meters per second, and I want to know how long he's in the air and how far away from the base of the cliff he's going to land. The first thing I want to do in all of these problems, horizontal projectiles, is to draw a picture. So I'm going to draw the cliff. It's 80 meters high, and he's running off the edge of it at 18 meters per second. When he does that, he will come to the ground. He'll take that sort of path, and we want to know how far from the base of the cliff he lands, how far away from the base of the cliff, and also how long he's in the air. When we do problems like this, I hope you've already learned that this is two-dimensional motion. There's two dimensions going on. There's a y dimension and there's an x dimension. And we also now know, based on what we've learned from previous videos, that the motion in the x dimension and the y dimension do not affect each other. And that is the major league point to all projectile problems, is that the x direction and the y direction are completely independent. They do not affect each other. So that means this dividing line is very important. X stuff doesn't cross into the y stuff doesn't cross into the x. We're going to now list the variables that we're going to have for each one of these, and the question is, in the y direction, with this projectile, with this Wile E. Coyote falling to the ground, this is motion. And the first question we need to ask ourselves when we have motion is there any acceleration? And the answer for the y question is yes, there is acceleration. There is acceleration because of gravity. Gravity is pulling downward, and anytime you have gravity, that will cause things to accelerate in a downward direction, y direction. So there is acceleration. If there is acceleration, hopefully you remember that we solve those problems with kinematics, which have the variables a, t, vi, vf, and delta d. And I'm going to make a little change for projectiles because we have two dimensions. I'm going to put a subscript y on all of these things. So that's in the y direction. In the x direction, I'll ask the same question. In the x direction, velocity in the horizontal direction, is there any acceleration? Well, if we think about it, the reason there's acceleration in the y direction is because we have a force going on. If you apply a force to an object, it will cause it to change its speed as long as that force is unbalanced. We'll talk about that when we talk about forces later. But the question is, if forces cause speed to change, is there any force acting in the x direction once Wile E. Coyote leaves the cliff? And as long as we can neglect friction due to air resistance, the answer is no. And in this class, we are neglecting friction due to air resistance. No forces in the x direction, therefore there's no speed change in the x direction. We have constant velocity going on in the x direction. And if we have constant velocity, hopefully you'll remember that we solve those problems using the equation v equals d over t. So all of our variables on the x side are v, d, and t, only three of them. And I am going to make a subscript x on all of these to tell myself that they're in the x direction. Remember, x motion does not affect the y motion. That means that this stuff does not cross over to this side, and this stuff does not cross over to this side. This is 1960s again. We got segregation going on. These guys don't like these guys. We don't cross back and forth. Make sure that the x stuff stays on the x side, y stuff stays on the y side. All right, so to work the problem, first thing we need to do is split the information into x and y because they are independent. They don't like each other. And I'm going to even go as far as to require you to split your paper in half down the middle. And we're going to do x stuff on one side, y stuff on the other. You don't have to do it on these two sides. You can flip-flop it if you want to. That's okay. Remember, in the x direction, there is never any acceleration. And in the y direction, y is always a free fall problem. Y direction is always a free fall problem because of gravity. Gravity is causing to accelerate. Okay? Because that's the case, you might be able to see now that this really isn't very complicated. It's everything we've already done before. We've done free fall problems before. We've done constant velocity problems before. Now they're both happening at the same time in the same object, but they don't affect each other, so we're going to solve them both at the same time independent of each other. Well, almost independent of each other. Two guess methods going on at the same time. So let's do the g and the u of both sides. I know I'm going to have vx, dx, and tx over here. With this problem that we have, do I know velocity in the x direction? Yes, I do. This 18 meters per second is my velocity in the x direction. Let's label a few more things while we're here. This delta dy is here. That's the height of my cliff. That's the height from which we're falling. I know that this distance right here is distance in the x direction. That's also referred to as range in many of the problems that we'll have. If you're asked for the range, that's what they're looking for. Okay, so Vx is 18 meters per second. Do I know dx? No, I don't. That's what they're asking me to solve for, actually. How far away from the base of the cliff? Looking for dx. How long is he in the air? Well, that's time. I don't know dx, and I don't know time. I know my equation over here is going to be v equals d over t, and I am going to put subscript x's down here, so I know that these are all x variables. And you might notice that I cannot solve this equation right now because I have two unknowns. So I have to go to the y side. And let's name all of our variables for the y side. A, t, vi, vf, and delta d. And let's run down that list. A in the y direction, if it's a free fall problem, that's just gravity. A is negative 9.8 meters per second squared. Time, we don't know. Vi in the y direction, again, it's a free fall problem. And if it's just a free fall and we're starting out horizontally, the question is, how much of this velocity is going in the y direction? Well, the answer is none of it. Therefore, the initial velocity in the y direction is 0, which is similar to many free fall problems that we've done. As long as we're just dropping something, the initial velocity at the top is 0. And this will always be the case for horizontal projectiles. If it's launched horizontally like this, Vi in the y direction will always be 0. Vf in the y direction, they don't tell us, and most of the time we won't know that one, at least in this class. Delta D in the y direction, we found that's 80 meters. And you might have figured out by now that since we will be falling down and not up, then this 80 should be labeled negative. Equation. This is kinematics. We have two unknowns. Question is, which one do we want? Well, we care about time because that's the one they're asking for. And if I care about time, I don't care about VF. So I'm looking for an equation that has time and not VF. And that equation happens to be delta D equals VIT plus 1/2 AT squared. And here's the secret. In this particular class, not in all other physics classes you can take, that's going to be your guy for a horizontally launched projectile. Not with projectiles launched at angles, but with horizontal, that'll be your dude. You can memorize that if you want. If you don't want to, if it'll mess you up, that's fine. You can keep looking for equations just like we always have, and you'll get the same one. Also notice that if VI is always 0 for a horizontal projectile, that makes this term 0, which means it goes away, which means effectively what we have is this equation. So now let's substitute and solve. Delta D is negative 80. 1/2 times negative 9.8 t squared. Half of negative 9.8 is negative 4.9. Divide both sides by negative 4.9. T squared then, if you calculate that, gives you 16.3. I don't want t squared, I want t, so I'm going to take the square root, and t gives me about 4 seconds. 4 seconds. We're in the air for 4 seconds. Still got one thing I'm looking for though. dx. How long or how far away do we land? So you might say, well, let's go over here and solve this. Well, I still can't solve this because I still have two unknowns. And that's where I get to the only caveat to this separation. Everything x and y are separated except for the time. X guys don't like Y guys and vice versa. Time is the only messenger that brings peace to both sides, and time is the only one that can go across. And here's the reason why. It's not really an illustration. Just think about it. Last time you walked off a building and were a projectile yourself, which I hope that didn't happen, how many times did you hit the ground? Once or twice? It was just once, right? In other words, you complete the x dimension of your motion in the same time you complete the y dimension. You only hit the ground one time because time in the y equals time in the x. And from now on, because of that, I'm only going to write t, not ty and tx. So I'm going to drag time across here, put it in, 4 seconds, which means now I can substitute and solve this equation. 18 equals dx divided by 4, understood to be under 1, over 1. Cross multiply or multiply both sides by 4, and you get 72 meters for distance in the x direction. So when he does this, it takes him 4 seconds to get to the ground, and he moves 72 meters in the x direction.